Good morning, students. So today we are going to discuss the last unit in the semester. So this is about angular momentum, and we are going to discuss the properties of angular momentum in this class, and the eigenvalues of angular momentum, and the ladder operators and their algebra. So in this class we are going to discuss these two titles. And syllabus goes like this. We have a syllabus of angular momentum, which goes with eigenvalue spectrum of general angular momentum, which we are going today, and ladder operators and their algebra, matrix representation of angular momentum, spin angular momentum, addition of angular momentum, Clebsch-Gordan coefficients. Okay, so CG stands for Clebsch-Gordan coefficients, symmetry and antisymmetry of wave functions, construction of wave functions, and Pauli's exclusion principle. Okay, so this syllabus has been divided into two parts. One is this is about angular momentum, another one is about symmetry. So there's a connection between symmetry and angular momentum. So whenever we look into symmetry, there exists angular momentum, especially rotation symmetry. Rotation symmetry, in the sense it is invariance in space. So whenever we look into classical mechanics or in quantum mechanics, and we have a smaller particle which revolves around the bigger particle. So this is called the rotation symmetry. And if it is so, the angular momentum is conserved. So we think about only equation of motion, the particle motion, which is constant, considered to be constant. So here the angular momentum is conserved. So we already know about the planets which revolves around the sun. So we know. So this goes with the constant of motion because angular momentum is conserved here. So whenever we talk about classical mechanics, immediately we think about the quantum angular momentum. And also this can be applied for the quantum mechanics because we think about the atoms, the electrons revolve around the nucleus, the motion of the nucleons. So which all go with only with the spherical symmetry. So they are all spherical symmetry. And spherical symmetry, immediately we could think about the equation V of r vector equal to V of r. So this is invariance in space. So not only in quantum mechanics, in all the other subjects also this will play a major role. Not only in quantum mechanics and classical mechanics, which we have already studied earlier, but it plays a major role in all the other subjects. For example, if we take EMT, electromagnetic theory, probably you would have studied about the Poynting vector. Poynting vector S equals E by mu naught with a cross product of magnetic field. So E stands for electric field and B stands for magnetic field. This Poynting vector S, which is perpendicular to E and B. So this is the direction of the propagation of the wave, light. So we are talking about S in the sense this is power per area, energy per area. So in fact, particularly we can say that this is momentum operator. This is momentum vector. Suppose we are going to multiply with the position r vector, we will get angular momentum. So S is equivalent to angular momentum. So what we call this as density vector. So momentum density vector, energy density vector, people will say. So in EMT also this will play a major role. Then in many areas, especially in day-to-day life, we have a whirlpool, we have hurricane, so those all they depend on only angular momentum. For example, if we go merry-go-round, so like flywheel rotation, so they all will bring up the concepts of angular momentum. So in almost all the areas, engineering subject also, this angular momentum will play a major role. So actually we think about angular momentum, immediately we think only the classical mechanics and quantum mechanics. But it will play a major role in all the other subjects. So whenever you think of the particle, small particle, which revolves around the bigger particle, immediately we will think about only angular momentum. So okay. So with this introduction, we are going to discuss today the eigenvalue spectrum of general angular momentum and ladder operators and their algebra in this class. So we are going to find out the eigenvalues and eigenfunctions of L squared and Lz. Your L stands for orbital angular momentum. So capital L stands for orbital angular momentum. Lz stands for the component of angular momentum. Okay. So we are given more importance about L squared and Lz. So both are given importance. L squared and Lz. We are giving importance for L squared and Lz. Okay, we will see later why it is so. So capital L stands for orbital angular momentum. Lz goes with the component of angular momentum. Okay. So another very important thing is capital L. Capital L, which says that the angular momentum, as I said just now, the unit of L will be your Js, joule second. And of course we know the unit of h bar, the reduced Planck constant or Planck constant, which is nothing but your Js. See, both are given importance. Okay, L has a unit which is same as unit of your h bar, and of course E equal to nh, we know already. Okay, E equal to nh nu. N goes from 1 to 3. So E equals h nu. So we have to give importance for the angular momentum. It's equivalent to importance to the energy. So whatever the importance for the energy, it's exactly equivalent importance for the angular momentum. So angular momentum is very, very important concept in quantum mechanics. So this is what I want to say. Okay. So the angular momentum of atoms and molecules are given importance like energy, since it gives some physical significance of a mathematical function which we are going to look into for one electron atom. The angular momentum of L is quantized. We are going to look into whether it is quantized or not. So it is quantized in the sense both magnitude and direction with the following relation. So we are going to obtain this relation. So this is the expression for eigenvalue of the square of the angular momentum. So which is very, very important one, which we are going to get the expression. So L squared equals h bar squared L into L plus 1, and it says that this is quantized, and small l goes with orbital quantum number. Small l is orbital quantum number. Capital L is orbital angular momentum. So for L equal to 0, L equal to 1, L equal to, so it's a quantized. It is quantized one. Okay, that's why it is called angular momentum is quantized. So we'll have discrete values. Okay, L squared is the square of the orbital angular momentum about the center of the atom. Okay, so as I said, suppose if we have a particle, small particle which revolves around the bigger particle, the angular momentum will be exactly like this, perpendicular, if it is like this. Okay, the motion is like this, you have an angular momentum will be perpendicular to both r and p. So r cross p is nothing but your L. Okay, r vector cross p vector will give you L vector. So it's a vector quantity. But in quantum mechanics, it is an operator. Like position operator, we have position operator, we have energy operator, Hamiltonian operator. Okay, and all those things are operators, all dynamic variables, and angular momentum also is an operator in quantum mechanics. We have to give equal importance for the energy, see, for angular momentum with energy. And another one, the component of Lz will be ml h cross. Again, it is quantized. So we are going to get the expression for eigenvalue of L squared and Lz. We are going to get the expression L squared and Lz. Lz is nothing but your ml h bar. Okay, ml h bar. ml stands for magnetic quantum number. So which depends on the values of L. Okay, and values of L will depend on n. So n, L, m, very, very important. For a specified values, for L equal to 1, ml will be minus 1, 0, 1. Okay, for L equal to 1, we have minus L to plus L through 0, as I said earlier. So for L equal to 1, ml will be minus 1, 0, 1. For L equal to 2, it will be, ml will be minus 2, minus 1, 0, 1, 2. We have 5 values. Okay, so they are all discrete values. They are all quantized. Okay, they are all quantized values. Okay, so these two expressions we are going to get it today. So as I said, so eigenvalue of your L squared will be this one, eigenvalue of your Lz will be this one. And we know already, as I said just now, this is about spherical symmetry. With the introduction, as I said, this is about spherical symmetry, correct? So whenever we think about spherical symmetry, V of r vector equal to V of r, we'll be using only what is this one? Radial part and angular parts. We'll be using the wave function exactly with the help of spherical polar coordinates. Okay, with the product of radial part and angular parts. Okay, now the angular momentum of the component is expressed as, so as we know that L is equal to minus IH cross d by d phi. So this is the operator, expression for the operator of the component of L is given by minus IH cross d by d phi. So operating on both sides by psi, that will give you L z psi, which is equal to minus IH cross d psi by d phi. Okay, is it okay? Where psi, as I said, psi is a spherical polar coordinates. Psi is a spherical polar coordinates. So as I said, psi depends on radial part and angular part. So psi can be written as r theta phi, which is equal to minus IH cross r theta. So d phi by d phi, as I said, because it depends only on phi. So I have pulled r theta as constant, I have pulled out. Is it okay? Come on, I repeat. See, instead of psi, you substitute r theta phi on both sides. So you are going to substitute r theta phi here, but it depends only on phi. So you can pull r and theta out. So d phi by d phi. The solution of this equation 5.4 is given by this. Phi equals a e power. We are going to assume a e power I ml phi, and also we are going to derive later. Okay. So now just to differentiate with respect to phi, this one. So we will have this. We know already that phi equals a e power I ml phi. We know already. So that's why we can write this equation as I ml phi. So d phi by d phi equals I ml phi. Is it okay? Now substitute this expression 5.7 in 5.4. 5.4 is given by this. So L is at psi equals minus I cross d psi by d phi. So instead of d phi by d phi, you can substitute I ml phi. Is it okay? So you have L is at psi, which is equal to minus IH cross r theta. Instead of d phi by d phi, you can substitute I ml phi. So I squared, that will give you minus 1. Already one minus is there. So you will have plus ml h bar r theta phi. So instead of r theta phi, you can substitute psi. So you will have L is at psi equal to ml h bar psi. Okay. So in terms of Dirac notation, we can write L is at operating on ket psi will give you eigenvalue. ml h bar is an eigenvalue with a ket psi. Is it okay? So this is the eigenvalue equation of Lz. The eigenvalue is given by ml h bar. It's a quantized one. Okay, it's a discrete value and it's a quantized one. And we have ml equals, as I said, minus L to plus L through 0. Okay, the wave function psi of an electron is the eigenfunction of Lz having the eigenvalue ml h bar. This is the expression for the quantized value of Z component of angular momentum of an atom. So we have derived one part. So our aim is to find out the expressions for Lz and L square. So we have found out the expression for Lz. Okay, eigenvalue equation for Lz is given by this one. Eigenvalue is given by ml h bar. Okay, of Lz for Lz. Is it okay? Now we'll go for the expression for eigenvalue equation of L square. See, our aim is to find out the eigenvalue expressions for L squared and Lz. We have completed one part, Lz. Now we are going to look into the other one, which is nothing but L squared. So for spherical polar coordinates, we know that L squared psi is given by this equation. We know already this. So earlier we have studied in hydrogen atom the problem itself, that is given by L squared. L squared operating on psi will give you this. Of course, psi with the spherical polar coordinates, you can write this as r theta phi, radial part and angular parts. Okay, so it depends on theta and depends on phi. I can pull r out. So simple one. So minus h bar r, you write this equation as it is. Okay, is it okay? And here in this part, we can pull phi out because it depends only on theta. So I have pulled phi out. In the second part, we can pull theta out. Okay, we can pull theta out. Okay, because it depends only on phi. Is it okay? Now we know that phi equals a e power iml phi. So just to differentiate this equation, because we are going to get second differentiation of phi. So just to differentiate this, you will get this expression, correct? ai ml e power iml phi. Again you differentiate this one, you will get a, already you have iml, then again one more iml, you will get iml whole square e power iml phi. And if you simplify this one, you will get minus ml squared pi. Is it okay? I squared minus 1, so you will have minus ml squared. A e power I ml phi will give you 5. So you can write this equation. So instead of this, you are going to substitute I ml squared pi. You are going to substitute. So substituting the value of d squared pi by d pi squared in that expression, we will have. So instead of this, we are going to substitute this. Okay. So this can be again simplified. Now it depends only on theta. So I can pull phi out. Okay, here phi out. So I can pull phi out because again it depends on only on theta. See here, look at the expression in the first term and second term. It depends only on theta. Depends only on theta. I can pull phi out from both the terms. So I have pulled out. So minus h bar squared r phi multiplied by this expression. Okay. So this bracket expression can be written as minus L into L plus 1 theta. Again we have seen in earlier classes when we are discussing about when we are discussing about hydrogen atom. Okay, minus L into L plus 1 theta. So this expression can be written as minus L into L plus 1 theta. Your L stands for orbital quantum number. Okay, so this term is nothing but your L squared psi. So L squared psi can be written as, instead of this term you are going to write minus L into L plus 1 theta instead of this bracket term. So like this. So you have L squared operating on psi will give you minus h bar squared r phi minus L into L plus 1 theta. Now just minus into minus plus L into L plus 1 h bar squared r theta phi. So instead of this you can write as psi. Your L into L plus 1 h bar squared is the eigenvalue of L squared. So this is eigenvalue equation of L squared. Okay, this is eigenvalue equation of L squared. So and eigenvalue is given by L into L plus 1 h bar squared. Again as I said, and this is a discrete one, quantized one. Okay, the angular momentum is quantized. So we have seen so far we have seen two things. One is the eigenvalue expressions for L squared and Lz. So Lz goes with ml h bar and L squared goes with L into L plus 1 h bar squared. So both are very important one. So we can say that they are quantized. So we will have only discrete values. So this is the quantized value of the square of the angular momentum of the atom. Okay, any doubt? So these two expressions are very important. Okay, the another method are also there. So we have seen only one method using spherical polar coordinates, which you have already studied. Now we are going to see this expression most probably after 2 or 3 slides. In detail we are going to see, and we are going to take the expressions of ladder operators. What we call this is ladder operators, raising operators and lowering operators. We have already seen this earlier in studying harmonic oscillator, raising operator and lowering operator. And in angular momentum also we have raising operator and lowering operator, which is given by this expression. L plus stands for raising operator, which is equal to Lx plus ILy. Lx is nothing but one of the components of your L. Ly is the y component. So Lx plus ILy. L minus is a lowering operator, which is given by Lx minus ILy. So sometimes it's convenient to write raising operator, lowering operator in this way. It is convenient. Okay, instead of studying always Lx, Ly, so we can go with the raising operator and lowering operator. Sometimes it is convenient. Okay, now we are going to use the raising operator and lowering operator in this expression, and we are going to solve the eigenvalue equation. Okay, it's simplest method. We'll see without solving spherical polar coordinates. So earlier we solved spherical polar coordinates, correct? So now we are going to have another method, which we are not going to deal with the spherical polar coordinates. Instead we are going to deal with only with the raising and lowering operators. So just L minus L plus. So there are operators. Okay, L minus L plus. So instead of L minus, you can substitute the expression for L minus will be Lx minus ILy. L plus will be Lx plus IL. Okay, so we will multiply. So Lx multiplied by Lx, that will give you Lx square. Simple one. Now Ly multiplied by Ly, that will give you you have minus and I square will be minus 1. So plus you will have, so plus Ly square. Simple one. Now we'll go for Lx with ILy, Ly with ILy. So Lx with ILy will give you ILx Ly, correct? So we will have to orders in quantum mechanics. When you are going to deal with operators, orders matter. So very important one. So we should not change the order. So Lx with ILy. Okay. Then this one will be minus. You have ILy with Lx. So ILy Lx. Now Lx square, Ly square. You just pull the common term I out. So remaining term will be Lx Ly minus Ly Lx. That will give you answer as Lx comma Ly with the commutative bracket. Correct? A comma B equals AB minus BA. Using that, so we have this one. Okay. So the first two terms I have written exactly like this. Your Lx Ly is nothing but IH cross LZ. Okay. Lx Ly, the commutator, like XPX, which you have already studied. Okay, in uncertainty principle. So here also we have the value of commutator of Lx Ly will be IH cross LZ. Don't forget, we will have to use the cyclic permutation. Suppose you have Lx, you have Ly, you have LZ. So now we are talking about Lx Ly. The answer will be plus IH cross LZ if it follows a cyclic one. Suppose if it goes on the other way around, then the answer will be minus I. So which you have already seen earlier. So you have Lx comma Ly with the commutator will give you IH cross LZ. Your I into I squared minus 1, so you have minus H bar LZ. And of course we know that the square of the angular momentum is given by, in terms of components, as Lx square plus Ly square plus Lz square. So we need only Lx square plus Ly square. So you pull this term out. So that will give you L squared minus Lz squared. Instead of these two terms, we can write this as L squared minus Lz squared. Okay. Is it okay? So now we need to have only L squared. Our aim is to find out the expression for L squared. So L squared equals Lz squared. Okay, L minus L plus and plus H bar Lz. Okay, is it okay? I have pulled these two terms that side. I have pulled these two terms from right hand side to left hand side. So we will get the equation 5.10. Now L squared operating on psi. L squared operating on psi will give you this expression. Same thing. L squared operating on psi will give you Lz squared operating on psi, L minus L plus operating on psi, plus H bar Lz operating on psi. And of course Lz squared psi, just now we have seen. So that will be your ml squared H bar squared psi. We have already seen this one. Your H bar Lz. So Lz psi, that will give you again ml H bar. One H bar is already there. So you have ml H bar squared psi. Now look at this term. You have L plus operating on psi. Then we will have, see, L plus operating on psi will be L minus. Correct? L plus operating on psi, that will go higher value. Suppose that higher value, that L minus will operate on higher value, give you again same value. So the answer will be 0. I repeat, see, ladder operator will operate on psi, will lift one thing up. Again L minus is there, again it will come down. So there will be no operation at all. So that's why termed as 0. Now we have these two terms. Okay. Now very important thing is, the highest eigenvalue of Lz will be H bar L. When you are talking about the highest eigenvalue of Lz will be H bar L. The highest eigenvalue. Highest eigenvalue Lz will be H bar L. So you can write this as H bar L. So that will give you L squared H bar squared psi. And here also you have ml, answer will be your L H bar squared psi. The highest eigenvalue of ml will be your L. Highest eigenvalue. So we can pull L out. Okay, you can pull L out, L plus 1 H bar squared psi. So this is the expression for eigenvalue of L square. Very simpler one, using quantum mechanical angular momentum ladder operators. Is it okay? So L squared equals L into L plus 1. Okay, H bar squared. One H bar squared is missing. Okay, your L squared will be H bar squared L into L plus 1. So eigenvalue of L square. Is it okay? Now summary. The angular momentum eigenstates of a particle are characterized by two quantum numbers L and Ml. So L is orbital quantum number, Ml is the magnetic quantum number, and the quantum number L determines the total angular momentum, which is nothing but very L square. L square will be L into L plus 1 h bar square. And Z component, we are taking only Z component Lz. Why can't we take Lx and Ly? It's a very important one. So earlier, before 1930s, and they took only Lx as the reference one. So after the application of magnetic field, people have taken the reference axis as Z. So that's why it's termed as Lz. So Lz is given importance because this is exactly reference axis of application of magnetic field. So the moment when you are going to apply the magnetic field, and of course Ml will play a major role. Okay, that reference axis is nothing but in the Z direction. So that's why we are giving much more importance for Lz, not Lx and Ly. Is it okay? So this is the reference axis of application of magnetic field. That's all. So for given L, Ml ranges from minus L to plus L, separated by the integers. So all are integers. That's why we are able to get quantized energies. So all discrete energies.